In Unit 2, we spend a lot of time looking at intramolecular forces. The prefix intra means within. When we're talking about intramolecular forces, we're talking about bonds, including covalent, ionic, and metallic bonds. Today we will be talking about intermolecular forces. The prefix inter means between, so we will be looking at the forces that occur between molecules, or between ions and molecules. Intermolecular forces are not bonds, so it is very important not to call them bonds. Intermolecular forces are much weaker than bonds are. They result from weak electrostatic attractions and as such are governed by Coulomb's law. Intermolecular forces are essential for life. Without them, we couldn't have this, or even this. Here are some of the most important intermolecular forces. We'll talk about them one by one. Ion dipole forces are one of the strongest of the intermolecular forces. They result from electrostatic attractions between an ion and a neutral molecule that has a dipole. An ion and a polar molecule, like water, align so that the end of the molecule that is positively charged faces a negative ion, and the end of the molecule that is negatively charged faces the positive ion. Imagine dropping a chunk of sodium chloride in water. The ions will separate, and as they do, they will be surrounded by water molecules. The negative end of the water dipole, i.e., the oxygen, which has a partial negative charge, will orient itself so that it is next to the positive sodium cation. The positive end of the water dipole, where the hydrogens are, will orient themselves towards the negative chloride anion. Take a close look at this picture. You'll be seeing things like it again and again. In general, the stronger the charge, the stronger the ion dipole force. For example, the ion dipole attraction between magnesium 2+ and water will be greater than that between lithium plus and water, because magnesium has a 2+ charge and lithium only has a 1+ charge. Likewise, the smaller the radius of the atom, the stronger the intermolecular force will be. The intermolecular force between lithium and water will be greater than that between sodium and water. Both have the same charge, but lithium is a much smaller ion. It also shouldn't surprise you that the stronger the dipole, the stronger the intermolecular force. All of these phenomena occur because of Coulomb's law. The next type of force is a dipole-dipole force. Dipole-dipole forces are attractive forces that occur between the positive end of one polar molecule and the negative end of another polar molecule. These are weaker than ion dipole forces. Let's look at how they work. Remember that polar molecules have an uneven charge distribution. One side of the molecule is more electronegative than the other side, and this creates a partial positive charge on one side and a partial negative charge on the other. Molecules arrange themselves to minimize the forces of repulsion and to maximize the forces of attraction. And this is what is shown in this picture. The green arrows represent the attractive forces, and the gray ones represent the repelling forces. The dipoles are arranged so that there is more attraction than repulsion. Dipole-dipole interactions account for some very interesting properties that we'll explore in more detail later. For example, molecules that have dipole-dipole interactions have higher melting points and boiling points than nonpolar molecules do. This is because it takes more energy to separate the molecules from each other. Now let's talk about hydrogen bonds. Now before we get much further, I need to clarify that hydrogen bonds are not bonds. Hydrogen bonding is actually a special type of dipole-dipole force. You can think of it as extreme dipole-dipole. Hydrogen bonding occurs when a molecule contains a hydrogen atom bonded to nitrogen, oxygen, or fluorine. These are the three most electronegative elements, and when these elements are covalently bound to one or more hydrogen atoms, the result is a very polar molecule with highly concentrated partial charges. These very polar molecules will interact with similar molecules. Those little hydrogen atoms with the partial positive charges on them will become very attracted to the lone pairs on fluorine atoms or oxygen atoms or nitrogen atoms that are part of other molecules. This strong attraction is called a hydrogen bond. It is an intermolecular force. Hydrogen bonds are often represented by dotted lines. Now, I want to say this one more time. Even though the term hydrogen bond has the word bond in it, a hydrogen bond is not a bond. It is a special type of dipole-dipole intermolecular force. Although hydrogen bonds are one of the strongest intermolecular forces, they are much, much weaker than the forces found in ionic, covalent, or metallic bonding. You also need to remember that just because a molecule has an oxygen or a fluorine or a nitrogen in it does not mean it can form hydrogen bonds. The hydrogen needs to be in the right place. It needs to be directly attached to a nitrogen, oxygen, or fluorine atom. If the hydrogen is attached to something else, like a carbon atom, it will not form a hydrogen bond. For example, this molecule, formic acid, has one oxygen that is covalently bonded to a hydrogen. This part of the molecule, which is circled, is capable of forming hydrogen bonds. And this picture shows how. By contrast, this molecule, which is called dimethyl ether, is not capable of hydrogen bonding. Even though it has an oxygen and several hydrogens in it, they're not in the right place. The hydrogen needs to be directly connected to the oxygen in order to be able to hydrogen bond. So, in summary, the molecule on the left is capable of hydrogen bonding because it has an oxygen directly attached to a hydrogen. The molecule on the right is not capable of hydrogen bonding. Sometimes molecules will form hydrogen bonds with other hydrogen bond formers that are just like them. This picture shows water molecules which are capable of forming hydrogen bonds with other water molecules. Here's another example. This is methanol. As you can see, it is capable of forming hydrogen bonds with other methanol molecules. Methanol and water can also form hydrogen bonds with each other. We can see that both of them have oxygens that are covalently bound to hydrogens. Some molecules, like this one, can't form hydrogen bonds themselves. However, they are able to accept them if a hydrogen bond former comes into contact with them. This oxygen and these fluorine atoms are very electronegative, and they also have lone pairs that hydrogens from hydrogen bond formers would love to grab onto. But even though they can accept hydrogen bonds, they cannot form them themselves. Hydrogen bonding leads to some very interesting properties. For example, melting points and boiling points are much higher than those of molecules that have similar size or shape or polarity. Let's take a look at the boiling points of our hydrogen bonders and their analogous compounds. And by this we mean similar compounds that form with other elements of the same family. See how the boiling points for the molecules that form hydrogen bonds are much higher than those for the molecules formed with elements that are not nitrogen, oxygen, or fluorine. The stronger the intermolecular forces are, the higher the boiling point. We will talk about this more later. The next type of intermolecular force is London dispersion forces. The reason ion dipole, dipole-dipole, and hydrogen bonding occur should now be pretty intuitive. Positive things are attracted to negative things. But intermolecular forces can also occur between nonpolar molecules. How can this happen if the molecules don't have positive ends or negative ends that are able to attract each other? The answer is London dispersion forces. London dispersion forces are the weakest of the intermolecular forces. They occur in all molecules, even polar ones, and they happen because of how the electrons move in an atom. Imagine electrons moving about in clouds of probability. Every once in a while, just by chance, the distribution of electrons on a molecule may be uneven, and there may be more electrons on one side of the molecule than there are on another. You'll get a temporary dipole. That means the molecule will become polar for just an instant. If this molecule is very close to another molecule, the other molecule may also be affected, and the Coulombic forces from the temporary dipole can induce a dipole in this neighboring molecule. These temporary dipoles will attract each other for a short period of time. London dispersion forces are very weak forces, and this is why the melting points and boiling points of nonpolar molecules are very low, often well below 0 degrees Celsius. However, there are some cases in which these forces can be pretty strong. The more electrons an atom has, the more loosely these electrons are held because they're farther from the nucleus. These larger, heavier atoms and molecules with big electron clouds are very polarizable, which means they have a greater tendency to form temporary dipoles. We can see this phenomenon in the halogens, which form diatomic molecules. Fluorine and chlorine exist as gases at room temperature. They don't have many electrons, and their molecules are not very polarizable. The London dispersion forces are weak. Bromine is more polarizable, and the London dispersion forces are larger. Bromine tends to be liquid at room temperature. Iodine is even more polarizable and more prone to forming temporary dipoles. It is solid at room temperature. The strength of London dispersion forces also depends on the molecular shape and the amount of contact area. More surface area means that the molecules have more opportunity to interact and form temporary dipoles with other molecules. Even when the mass is the same, shape matters. For example, look at these two molecules which have the same mass. The one on the right has a larger surface area. See how there's more area for contact and more opportunity for the temporary dipoles that are produced to influence each other. The shape of a molecule can also make a big difference. Take a look at these two fatty acids. Stearic acid, the one on the top, is a saturated fatty acid and is straight. Cis-oleic acid on the bottom has a bent shape. The London dispersion forces in the stearic acid are stronger than the ones on the bottom molecule because it is easier to stack these molecules and put adjacent molecules into contact with each other. The bent molecule on the bottom is harder to stack. We can see the effects of this when we look at the properties. Saturated fatty acids are solid at room temperature. They have stronger London dispersion forces. Unsaturated fatty acids are liquid at room temperature. Polymers are very long molecules that are comprised of smaller subunits called monomers that have been linked together in a very long chain. As you might imagine, because these molecules are so long, there's a lot of opportunity for temporary dipoles and London dispersion forces to occur, and the intermolecular forces between polymers can be quite strong. Polarizability is enhanced by the presence of pi bonding. As you may recall, sigma bonding is formed by head-to-head overlap between orbitals. In this type of bond, the electrons are fairly tightly held in the space between the two nuclei. By contrast, pi bonds are formed by the side-to-side overlap of p orbitals, and the electrons in these are delocalized and they're free to move. Hence, a molecule with pi bonds is polarizable. More pi bonding in a molecule means more London dispersion forces. There are other types of intermolecular forces that are variations on the ones we just talked about. For example, ions can induce temporary dipoles in nonpolar molecules. We call these intermolecular forces ion-induced dipoles. Polar molecules can also induce temporary dipoles in nonpolar molecules. We call these interactions dipole-induced dipoles. So let's summarize. Intramolecular forces with an A are the strong forces that hold atoms together within compounds. Intramolecular forces include covalent, ionic, and metallic bonds. By contrast, intermolecular forces are the forces between molecules, or between ions and molecules. Intermolecular forces are not bonds, so do not call them bonds. They are much weaker than bonds. However, they determine physical properties. We'll talk more about that in the next video. In order of strength, intermolecular forces include ion dipole forces, hydrogen bonding, dipole-dipole forces, ion-induced dipole forces, dipole-induced dipole forces, and London dispersion forces. The three that you will see most often on the AP exam are hydrogen bonding, dipole-dipole forces, and London dispersion forces, and it is essential for you to remember the relative strengths of each, and how strength can be influenced by molecule size and polarizability, surface area or contact area, and the presence of pi bonding.